to you was done in the context of pluripotent stem cell lines, because these have the great opportunities for differentiation and for this epigenetic and genetic reprogramming. We need shareable standards, so we need to have cell lines where we know what their properties are, what the phenotype of the adult individual was, and what the genome is. As we'll see in a moment, how important it is to know the genome of the cell lines you're dealing with, not just the reference genome. Anyway, the NIST and the FDA have started collaborating a couple years ago to establish standards for synthetic biology, for human cellular biology, and for genomics. So if you develop a new technology, new instrument, a new diagnostic service, it'd be nice if you could test that with a vial of cells of DNA. It's the same as the vial everybody else in the world has. That's what this standard is all about. So they established the genome model, and they looked around the world for a suitable cohort from which they could get cells of DNA, and they found one, as far as I know, which is the personalgenomes.org, which I helped start a decade ago, which is the only one that is a project which is open access in a safe and shareable way. And so they're using 8 trios, another modern trial, 24 samples, taking tens of thousands of vials available around the world. The project itself is international. There's 5 sites worldwide, and I encourage, basically, the relevance to you is I encourage you to take advantage of both the standards and the cell lines. These are available not only from this, but from Coriell in various different cell types, pluripotent stem cells, fibroblasts, T cells, and so on. And the reason that this is safe is because these individuals are consented for likelihood identification and commercial use. They have to get 100% on the exam, which is actually a higher score than you have to get to do human subjects research on your human subjects research exam for IRB. Okay, so we have, and you don't just have cells and genomes, you have really complex organism data on these individuals, like functional magnetic resonance imaging there. That's my brain. In fact, a number of these cells are mine as well. To get the idea. So, variants of unknown significance. This is a safety issue in a certain sense. Do you cause stress to a patient by telling them that they have a BRCA1 mutation that you don't know what is going to cause breast or ovarian cancer, or do you not tell them and put them at risk? So variants of unknown significance are very significant. You can test and principle variants of unknown significance in animal or human models. There's 3 animal models for testing. This rare individual was a double null for myostatin. At the time that it was discovered, you could only do an N of 1 study, and I think this happens in many interesting cases. In fact, to some extent, everybody in this room is an N of 1 that has a unique combination of microbiomics and genomics and other environmental factors. And so I think we need to get better at this. And the beauty of it is, rather than depending on correlation where you might lump together 10,000 people who are not really exactly the same, you change the causality, where you're really determining cause and effect by making point mutations or epigenetic changes. Now, in order to do this in an animal model here that confirm the high musculature and decreased body fat mass, decreased atherosclerosis in treated animal models, but you can also increasingly do it in human organoids. And these, in some cases, they achieve things that are hard to achieve in animal models and potentially to be much more scalable and low cost. So this is work from John Ingber's group and Kip Parker and our group and others, the Research Institute and other institutions, where you have about a dozen different complex tissues that are getting more and more complex and realistic every day. And it's a big change from basically the last century of cell culture, where you typically have a monolayer or most 2 layers on a plastic petri plate. But here you have mechanical forces in multicellular, such as you have bacteria, for example, in the log infect models. These are really something to think about if you're going into CRISPR, both epigenetic and genetic. I'll give an example that combines both of those, the epigenetic and the genetic. This was published in collaboration with William Hu and Kip Parker in Nature Medicine. And it's a typical case where you have a variant of unknown significance, where you have a severe cardiomyopathy, and you have one guanine there that is hypothesized actually being missing on the X chromosome. And the PATH mutation is hypothesized to be causal, not just correlated, but that's a hypothesis. You can test it by making a clean isogenic change in the genome. In this case, as I mentioned, we use these Personal Genome Project cells. This is PGP1, which is fibroblast derived from my left arm, turned into pluripotent stem cells, and then we make the Cas9 excisable. So we have great control over this Cas9, and then introduce guide RNAs and donor DNA, which is specific for this problem. So the Cas9 pluripotent stem cells is a generic starting point, but the guide RNA, the repair oligos, so it's a single-stranded oligo, it allows us to do homologous recombination, and then piggyback we excise the Cas9, and we have a clean genome that should have only 1 base pair difference. If we leave out the repair oligo, then we get non-homologous end joining at higher frequency, and in this particular case, we established several clonal cell lines, including one which is a normal control, a 1-base deletion of Fc, and then an 8-base insertion of non-homologous end joining. So, what does this look like? So, by all the criteria, the cardiolipin problems, the mitochondrial problems, the this morphology and the contractile nature. The normal, you can reconstitute from these stem cells a highly ordered cardiac sort of heart on a chip model, where there's beautiful repeating sarcomere organization, which is not found in the single HG deletion or the non-long joining alleles. And to complete that proves that this is the gene that's involved in the mutation. You can complement with modified messenger RNA, that is to say, introducing messenger RNA recovers most of the wild type function. Now, I kind of glibly said that we've changed one G base pair, and after discussion yesterday and today about all of the off-target effects, you might say, gee, that's pretty naive. What's wrong with this guy? And what happened is, in the period of time since I started my lab, when we used to really worry, but not actually check, or then later do PCR to make sure the mutation we made is the right one, that we'd be checking out 200 base pairs that we have. Because nothing of sequencing in the genome to make sure that they change one base pair and not the rest. And so Luna Yang, when she did this experiment, she sequenced two of the mutant clones, and then also did deep sequencing of population. So in the two mutant clones, there were zero off-targets, except for one, which I will claim is in a certain sense on-target for reasons we'll be at in a moment. And then if you look at the large population, you see about 5% off-target, which that is to say have 3 or more mismatches. And so that means that only 1 in 20 clones would be off-target. So it's relatively easy to get clones of cell lines that are 100% on-target and no off-target. The exception, and that then what makes this story even much, I think the two things are interesting here. One is the idea of using clonal cell lines as a way of cleaning up all the off-targets and cleaning up all the mosaicism and non-target. The second thing that's interesting here is that for technical reasons that aren't that interesting, the software that we wrote to check for off-targets used a standard reference sequence rather than the correct reference sequence, which is bigenome. Bigenome's been known since 2009, so there's really no excuse. But nevertheless, I'm glad we did it this way, because what we found was there was a SNP. So we were aiming for chromosome X, which is only one of the males, deleting a G. But on chromosome 5, there's a polymorphism that I happen to be heterozygous for, but the human reference in Zinbank is not heterozygous for it. And the consequence of that is that even though we were avoiding off by 1 and off by 2 mismatches, we happen to now get this SNP cause off by 2 and a very significant off-target of almost 37%. Let's just look at that a little more detail here. Since you're all connoisseurs of this off-target since yesterday, this is the guide RNA region we're targeting. This is the PAM sequence, which is unaffected. Here, the three off-target, which is the reference genome, and then this is where 2 are off-target, where I have a SNP, a heterozygous SNP, and you can see that, and you can the normal one is ancestral, and you can learn about it. And then you might ask, well, I said off-target doesn't matter if it's not in a oncogene or a tumor suppressor, so you can check to see where it's pretty far away from any gene, and it's a pretty big stretch. If you do a careful search, you can model every gene that's involved in cancer.